another draft science video, yes, and physics, and two slit, and I think it is worth going over, even though it's not directly related to, I don't need to explain the two slit experiment to defend the rest of, the substance of my argument regarding the nature of force unification, the fact that there's only one force. There's only one mechanism creating all expressions of something we call a force. So anyway, and that's this quanton idea, this idea that there's a fundamental particle that makes up the entire universe, and when it's freely moving, it's called energy. When it's trapped inside of a piece of matter, it's called matter. When it's caught in an orbit, and that's the only real distinction. Certainly its directionality is significant. Gravity only has meaning as energy when there's this imbalance, when you're being shadowed, something's blocking the force, is when the force reveals itself. So it's really, again, just about a imbalance in force that we call energy. The energy's still there, it's just that it's equalized, and equalized energy is nothing. So, plus 1 in this direction, plus 1 in this direction is 0. And its energy is only revealed when there's some imbalance in that relationship. When there's more going this way than there is going this way, we have an imbalance, and we have something we call energy. So anyway, that's the background of the connection this has to the theory fundamentally. So obviously things like, I would argue, just because of the mechanics of this system, light can't be bent by this force, because it is part of the force. Light is just the force, it's just quantons with a frequency coming at a specific period. And otherwise it's identical to the rest of the force mechanism. So it's gravity, it's just gravity with a frequency, and that's why it's identifiable. Clearly it would be invisible, I guess you could argue, if there was some equal frequency of gravity coming from the opposite direction. If there was a light beam coming at a light beam at exactly the same frequency, we might not be able to see. But obviously we can't see it, because then our eye would have to be projecting it, so you can't sense it. You couldn't sense that circumstance. There's no way to detect that circumstance, because the detector would have to be the emitter. Alright, now that's probably... nobody understood what I just said, but it is all important. But anyway, some people have posted some links, and so I did go watch some of this other mush. And, people have these different theories. The ether one I like, in the sense that at least people are conceding that there's not a nothing fabric, there's a something fabric. And so they talk about light as a transmission through an ether. And, that's close, but it's still no cigar, because they're not recognizing that, no, the ether is actually light, it's actually moving. The ether isn't a quiet substance, and light is the noise inside the quiet. No, light is just more of the noise inside of the noise, and it's just noise of a specific frequency, so we can detect it. We can pull it out of the noise, because we can identify it by its frequency. What else? So anyway, and so somebody did post to this. I think it's the Mel Gibson guy or whatever. That is his icon, which is really annoying. And his comments have disappeared, so I don't know whether he deleted them or what. Well, anyway, so and they do the multi, what do they call that? Screen. The screen with lines on it. They call it a whatever. I can't remember the name. they use for it. Well, anyway, and it creates this, instead of the two slit, pattern, it creates this idea of just a dot, a dot, a dot, all equally spaced, all of equal intensity, mostly. I mean, more intense in the middle, and then gets less intense as you go further away. And what's really happening is that depending on how many lines you have in your filter, so your filter would have a whole bunch of little lines, little slits, so to speak, they would be represented inside of here as the dark spaces. So there's really just a bunch of cancellations in between each dot. And that's the way the pattern is being created. So it's essentially the two slit, but they're all so fine, they're so small that you can't see them anyway. But anyway, that's part of it. Let's not bother with that part now. I just wanted to point out how easy it is to make mistakes, and how I've made a mistake in my video. In when I was talking about the two slit, and the idea of the force pushing, because, I'm trying to explain the stretching of the light. The way the light compresses in the two slit experiment. It doesn't just that it's getting spread out, it's actually compressing. The vertical component is disappearing. It's getting lost, and it's being forced into a horizontal component that's on one plane. So in a sense, it's not doing what it should do, which is the same thickness, just goes out wide. It's thinning and going out wide, and that's worth noting, I think. And so, I implied that the force is pulling the light, and obviously I don't believe that the force can affect the light. What's happening is the force is creating a circumstance where electrons are in certain orientations. And again, it's electrons that create all diffraction. There's no diffraction without an electron. You have to hit an electron, and the light has to be re-emitted at a new angle. So it's only these orbits. You have to have something that has an orbit in it, where it can capture the light and then release it in some different direction. So it's much like the way we use spacecraft to go around orbiting bodies to create new trajectories without having to waste fuel. So instead of turning by, wasting energy to turn, shooting a rocket to bend you in a new direction, that you can just use gravity to bend you in a new direction. Because what you gain going in is what you'll lose going out. So you'll gain some speed as you go into the gravity, and then you'll lose some velocity as you leave the gravity. But your direction can be anywhere. So if you want to do a U-turn in space, if you want to fly into space and go really fast, and now you want to, reverse your direction, you don't have to stop, turn around, and then re-accelerate in the opposite direction. You can just fly yourself towards the sun or something and just miss capture velocity, capture distance, stay outside of capture distance, and do a U-turn. Just use the sun to maintain your same velocity and just turn around. And essentially that's what's happening with light. Light is diffracted when it goes into an orbiting system, and it leaves in some different direction. And that's reflection and diffraction of light. It's often not the same photon even. The one photon goes in, a different photon comes out. And again, the photon is just a representation. It's just made of these quanta. And so it's quanta in, quanta out. And what can be changed is the frequency of the quanta out, how often they come out, or the period between them, or the direction can be changed. And that's the function of this orbit thing. That's the significance it creates, and that's why it creates everything in the universe. So I'm saying this simple mechanism, having two things orbit each other, creates all the complexity we see in the universe. All of it. Through that simple mechanism. Because that mechanism creates an imbalance in the energy field. And that imbalance will create more imbalance, will create more imbalance. It breeds an imbalance. Yeah, technically, practically. So anyway, in implying that, I'm just saying that someone could say, I mean, it's not like I overtly said the force is moving the photons, but I came close enough to that to be misleading, and so yeah, errors happen. And so I just noticed that this guy posted me to a video, and it's just this huge error in what the guy says here. And I just thought I'd point it out, just because it's such a, it's not an error that should be in a video. I mean, in this level of, the guy's not stupid. So anyway, it's this level of physics online. So he does this thing. So we're talking about one of these gradients. That's what they call it, a gradient. I think. And anyway, the idea of what happens here, and what happens if you shined white light through it. And he's saying that, okay, well, you'd end up with blue, yellow, red, and on your dots. And that's, no. What you'd end up with is these space, how to put this? See, because there is no dots. When you use white light, you don't get any dots. The whole thing just turns to shit. I mean, you don't get the pattern. And the reason why you don't get it is because the blues will end up being blue here, and then blue here, and then blue here, and then blue here, and there'll be one red here and one red here. So everything gets spaced different because there's going to be more incidences of blue photon than there'll be of red photon because of the period. But anyway, don't need to go into that. So anyway, yeah. So I mean, it is difficult to, especially off the top of your head, in this casual kind of conversation about physics, more casual, let's just call it. You can make mistakes. I mean, this isn't a scripted lecture, and so errors in verbiage can happen. So anyway, these old MIT, like, I don't know whether it's from the 60s or 70s or something, but they're kind of funny. I mean, they're kind of interesting. They're kind of useful. So this is so he was talking about doing this circular aperture thing, and I don't think it's terribly fascinating, but I mean, the idea of it is the same. I mean, you get exactly the same pattern. I mean, you could just cut a piece of this out somewhere, and you'd get the idea. But what I found interesting in this circular one is this is happening, and I don't know what this artifact is from. Because technically it shouldn't be there. This little subtle cross that's happening shouldn't be there. I mean, these aren't apertures that you can make bigger and smaller. These are actual holes in a piece of metal. So there's no imperfections. And you're just like, where is that coming from? But the trick is they're using two mirrors and then putting the laser through a lens, and I don't even understand what the purpose of the lens is. So it is a little bit. So this might be an artifact of the lens. Unfortunately, I don't know what the purpose of focusing a laser would be. It's already coherent light, so I don't. That one escapes me. I mean, I guess I'll show you a picture of that. I don't know if it'll show up or not, but the setup. Come on, YouTube. Little icons there. You should be able to do this. Come on, YouTube. Fucking bastard, son of a bitch, rat. Fucking creepy jerks. There it is. Oh, shit. Okay, well, that's good enough, right? You can see the lens quite clearly there. Come on, freeze it, baby. So laser. Look how big the laser is. Laser, mirror, and then there's a lens, and then there's the aperture, and then there's the screen. But what is this doing here? I mean, this laser beam is already a fine point. Why is it going through a lens? That one escapes me. I mean, except to spread it, I guess. So, which is kind of strange. So they're spreading the beam here onto a tiny aperture, which, I don't know. Yeah, I don't know about that one. Well, anyway, so that's what I'm figuring. This artifact is a byproduct of this cross that's happening here. That's what I'm figuring. Yeah. So anyway, all right. So what I wanted to get to. So what's causing this is the point, right? So whether we have a circular aperture, I'll draw both pictures just for the hell of it, or we have the regular slit style aperture. Excuse me. The other thing to understand is, I guess I'll go back to the other image. So when this is being shot across this distance, I mean, all of this, I mean, the lens is shortening the distance, I suppose you need for the screen or something, but at any rate, to be understood is that this light is just going this, it travels this distance, but I mean, this is a tiny slit, so that really the light, the actual light that's not being diffracted, is just hitting a tiny, tiny, tiny spot on the target. So the unaffected light is still going through. And again, remember, this is all about probability of where the light will end up, to use Feynman's terminology. So, I mean, this is where, like I would argue that, how does the photon know how wide the slit is when the photon's going to go through, say, the very center? There's a probabilistic obligation for it to do certain things. How if it kept going through the center, would it keep doing those things? Of course it wouldn't. It would go through the center, it would end up in the center. It would always end up in the center, no matter how narrow the slit is theoretically, if it's exactly the center. But that was what I'll try to explain. But that's something to understand, is that the light's going in straight lines, and it's coming out at angles. Well, angles spread like turkey feathers. But only a percentage of the light gets spread. 50% of the light, or whatever the number would be, doesn't get affected at all, goes straight through. So that's kind of a way to understand this, is that this is about an odds of hitting something first, and then when you hit something, what does it mean? So if you hit the electron, if the light goes through and it hits the electron, that's the implication, is now it's going to be bent. Or if it goes straight through and hits nothing, well then yeah, it's going to be part of that central maxima. That'll be the photon's fate. So even a photon going through the very center, theoretically, can go straight through, or if it hits an electron, it can be bent radically, depending on the disposition of the electron it hits. And so that's why I want to get into this what I think is happening is something like, okay, so you could sort of see it with this idea of the finger diffraction. So if you take a white screen on your computer and just hold your fingers together, you can see first this aura, this whatever you want to call it, this stuff, okay, this extra stuff outside of your finger, okay? Your finger seems to have a bunch of fudgy space around it, fog, whatever you want to call that, ether, stuff. There seems to be some stuff around your finger. And then when you look at that stuff, you can, you look at it, you can really see that it's lines that you can see. And then when you push them together is when you can really see that they're lines. But you can sort of see the lines even when you're just looking at your finger in the white light. But anyway, so indicating field lines. So I guess my argument would be is that all matter creates a field. It might not be a significant field in terms of you can't make things come to you. It's not magnetic or electric in some very strong way, but it exists. You're always producing a field. It's just not that it's not polarized, and it's not strong enough to do anything. Well, it has to be polarized to some extent. But it's just not. It's not a strong field. It's a weak field, but it's strong enough to orient an electron. Electrons are very sensitive to fields, okay? So, they use the electrons, to make the old TV screens, because you could take a little bit of magnetism and you can make an electron go anywhere. You could bend electrons really easy in terms of moving them about, but you can't move light about. So anyway, the argument I would make is that you can't bend light, so that's why Einstein's wrong. Gravity's not going to bend light, but you can. If light hits an electron, it can leave in a new direction. And that's the argument being made here, is the orientation of the electrons is being controlled by the matter. All matter is producing this edge, these field lines. So if you were to just make a simple drawing of them, they would be kind of flat, and then they get bolder and bolder in terms of their arc. So they're flatter, and then more arced, and then more arced. And this, they would be on all surfaces, would be creating these field lines. Now for a circle, it's exactly the inverse of this. So for a circle, the field lines would end up being centric. And but it's going to create the same circumstance will exist, in the sense that these electrons are going to all be, any electron in this field is going to orient itself to these field lines. So they're all going to be oriented in their character, in their position, based on these field lines. These field lines are significant in the sense that they'll control the shape of the electron. Whether it's spinning this way or spinning in some other direction will be dictated. Its orientation will be dictated by this field. So as a photon comes through, depending on which an electron in what position it hits, there's a probability of what electron it will hit, based on density and based on how these field lines are encroaching. It will diffract the light, coming out. So depending on what its orientation is, like I said, there's more of a pitch here than there is, on this field line. This one has many more angles on it. So and the angles are what's creating the pressure in this direction. So the laser beam's going from this to this. And the argument I would make is that's being created by this arc. The arc of the field line, this triangle, is what's pushing. So when a photon hits down here, what it's happening is it's getting pushed here. And when one hits up here, it gets pushed down here. So that's what's stretching this beam. And so as you move these field lines together, first you're just hitting, say, the edge of the, you have your laser light. You're just hitting these edges. So first the field lines start encroaching on the edges, and they just start to bend these edges down into that configuration. And because electrons have a certain orbital speed, that they have their own timing cycle, and it's the timing cycle, it's the size of their orbit, let's call it, that is going to dictate the position, this position. What's the position of the landing point will be decided by, again, another feature of the electron, but clearly a feature of the light coming in. The frequency of the light going in will decide these points. So, and that's what you find in the two-slit experiment, is change the frequency of the light, you change the points where where this angle will direct the light. So the angle of diffraction is decided by the frequency of the light, and it's always a diffraction. Let's see how to put this. But the fact that the light doesn't get, well, electrons by nature don't freely transmit. They're not like glass. They have to be in glass for them to be oriented in such a way that they will pass light that they'll reproduce it the same way. I can't. What's the word I'm looking for? That what goes in will be what goes out. But electrons don't really do that. They don't do what goes in, what comes out. They do what comes in, comes out in a different way. That's what a reflection is in a sense, right? The reflection isn't the light comes back at you. The reflection is it comes out at an angle similar to the angle it went in, but in the opposite direction essentially. It's the same. It's the same direction. Well, it's an opposite pitch. It was going that way, and now it's going that way, which is getting back to this X argument. It's lost its original direction, is doing a new direction. So it seems obvious that, well, that's what would happen here, is that these reflections are what we're calling diffractions, but it doesn't really matter what you call them. They're angle in, but a different angle, a different direction, same angle out. Well, it can't be the same angle, like I said, because the electrons have a different orientation. So we're not talking about electrons with the same orientation. If all the electrons had the same orientation, then it would be the same angle out, and then you wouldn't get this stretching effect. You would end up with a beam like this that might do this, but it would stay thick. It wouldn't get thin. All right, so I really think, I don't know if I have to go too deep into this, but the key point is, first, not all the light hits an electron. Second point, if it hits an electron, it will be diffracted. Its direction will be changed, and the change is going to be consistent with the idea that these electrons will have a probabilistic distribution. There'll be just as many on this side as there are on this side, and these arcs and these angles will all be consistent. And so I guess I wanted to get to the point where you're closing the slits as you encroach on this laser beam. To understand that is that the percentage of the beam that starts hitting this strongest angle, which is the outside angle, in here is straighter, out here is the strongest angle, and that strongest angle, gets to be maximized in the center strongest light of the beam. That's when you got the most of this happening. But obviously you're also now just inside of a tiny percentage of the beam, because your slit has gotten so small that you're much smaller. The slit is now much smaller than the beam size, so your beam is much bigger than the size, the little slit that you're taking out of it. But you've now maximized the influence of these strongest angles. So that's why you have the most stretching before the light becomes too weak to be perceived. Yeah, so I think that's enough of that. The rectangle diffraction is interesting because that's when you start to get the idea of what happens when these gradients, that ends up just being a matrix of dots. It's almost like a checkerboard, and what's being revealed is just parts of the checkerboard. And so in a rectangular diffraction, you get these bars coming here, but you do get this interesting, at the corners, these little, it's happening also. But anyway, but it's just so consistent with the idea that these are all these angles. It's just all these angles here that are deciding, which way the light will go. So anyway, it just seems clear to me the strength of the single slit under the right conditions, using coherent light. So let's understand also that that's a big difference in this experiment, is when they use a laser beam versus using the traditional. In the traditional two-slit experiment, you're supposed to use an aperture, which is just another slit, to, which widens the light, but also creates the cone in the sense that the light will be much more intense in here in the middle, and much weaker out here. So you have strong light and weaker light. Where with the laser, you're supposed to technically have a pretty consistent intensity of light throughout the whole circumference of the laser. And so I think that's why these diffraction patterns in the single slit especially look so much brighter, so much stronger with lasers than they do with the conventional methods. Because you get this conventional curve, when they just do the math, you end up with some, a thing that looks like this. Okay, this hugely disproportional peak in the middle. And that's I would say is true when you're presuming light of variable intensity. That is, the light coming in is more intense in the center than it is in the fringes. That would make sense. But with a laser, like I said, this is the strength of the light coming in is consistent throughout, and so this isn't nearly, it's more like this. And the key difference again between the single slit and the double slit is just the fact that in the double slit, this peak is half as big, so it's not as wide. It's just as strong, but just it's not as high. Well, it's not just as strong; it's half as strong. So that's what's deceiving people, is they're making comparisons between the intensity of this middle light and the intensity of this. But obviously, if you cut this middle light in half, well, then these look much more intense. And that's sort of the illusion of the double slit versus the single slit, is just the illusion of the fact that you've now reduced the central maxima by 50%, which has made everything else 50% brighter by comparison. All right, that's probably enough. I mean, the manipulations you can do with this kind of stuff is, you can sort of see it in this video, because he has the image and then he opens the aperture on the camera. So right there you see I don't know if you can see that, but it goes from this to shit. Well, anyway, what happens is the background you can see the background grays because he's opened the aperture, let more light in, and this pattern becomes more and more revealing. So it's like it's not there, and just by letting more light out, it's there. So those are all things you got to recognize going on. All right, so is this enough? But I think this is an explanation conceptually. It provides a concept to build on. And I think it's much more coherent than photons making decisions. No, the matter's making the decision. The structure of the slit is telling the photon where to go. The photon does nothing. Light obeys. Light does not decide, so to speak, as a general rule. Light goes from point A to point B unless some physical thing, matter, electron, tells it to do otherwise. And that's the reality. So it is the material that the slit is made out of that is dictating where the photon goes. The photon has no power. It has no character. Photons are really simple and really dumb. Where matter is still dumb, but much more complicated in terms of the forces coming out of it. And to just understand, you're constantly leaking these forces. The gravity comes in, it's coming out the sides. It's happening all the time. You're radiating directional changes in force all the time. And matter's doing that all the time. The stuff is coming in and it's leaving at different angles, depending on what velocity the object has. And whether it's acquiring acceleration or not is also a key element to that. When you're acquiring, especially when you're acquiring acceleration, you're emitting a lot of the other direction. So when you're being converted to going this way, you're emitting a lot of that way. And that way, especially. You're definitely emitting a lot of that way when you're being accelerated. That's what's accelerating you, probably, is the emission of that way. Anyway, so that's probably enough. Yeah, I just don't want to leave something out because I don't want to do a third double slit video for a little while. Anyway, so yeah, that's probably enough. And just on the general subject, I mean, the general idea is having some sort of rational conversation about what conclusions physicists have drawn over the last 100 years and what they base it on. I'm just saying, it's just sort of becoming obvious that it isn't based on much, and that if they try to find a different answer, they can find a different answer. And I can't say that this is absolutely the correct interpretation, but it's an interpretation that certainly has an air of plausibility. So anyway, but I mean, it does change this understanding. I mean, it's a subtle thing to say, okay, what's it matter whether gravity can bend light or not? And like I said, it only matters if you understand the idea of this field, this unified field, and that all the forces are an expression of this field of gravitons or quantons or whatever you want to call them, and that a photon is just a piece of that field that has a frequency. And that's sort of a great benefit, that we actually have a piece of the field that we can see. We can actually see a little piece of magnetism, so to speak, or a little piece of what's going on because of photons, because they have that frequency. And it's both confirming and it gives you a way of envisioning the idea. I mean, to me, gravity is really perceivable if I understand it. Oh yeah, I can see how all these photons are flying around. Well, why? And they seem quite benign and harmless. Why couldn't there just be a zillion tons more of this gravitons doing exactly the same thing? And that as long as the field is balanced, as long as I have as many coming this way as I have going that way, I can't tell they're here. Why not? So, anyway. So enough. So until next time, and such.